Hi everybody, this is Mark Weitzman. Welcome to my YouTube channel on theoretical physics. Today I'd like to continue with my QFT review blog, and I'm going to do, this is number 7, and I want to do a video on a problem in Z's book, QFT nutshell book. On symmetry factors. And this is an exercise on the book. It's on page 60. Exercise 1.7.2. And the exercise is basically to derive in scalar meson phi4 theory the amplitude for the following diagram. And the diagram is so it's two particles coming in with momentum K1 and K2, and going out with K3 and K4. This is the momentum space diagram. And the amplitude ends up being 1/2 minus I lambda squared. The potential is of course lambda phi to the 4th. And the integral of d4k 2 pi to the 4th I over k squared plus m squared. I epsilon I over k1 plus k2 minus k squared plus m squared minus I epsilon. So this comes from the Feynman rules. And the main thing we want to discuss is this factor 1/2. 2 is the 2, sometimes a half, I'm not sure, is the symmetry factor for the diagram. And most QFT books don't really discuss symmetry factors that much. They'll point out that this diagram has a factor of 2, and basically they'll say, well, you can switch the internal propagators of k and k1 plus k2 minus k, and so that makes it a 2. But it's sort of a hand-waving argument. The only book that I know of that does this really thoroughly and really well is Srednicki's book, QFT book. I think chapter 9 has long discussion on symmetry factors. They only occur when there are loops, and most theoretical physics students aren't going to go beyond a one-loop diagram and so on. So usually the symmetry factor when you have a loop is like 2 or 3 or something like that. But so that's why the books tend to ignore it. But it's interesting to see how it comes. Chapter 9, page 58. So Z starts, he gives the functional integral. Zj is equal to the integral. This is a path integral. I don't want to derive this or discuss this too much. I'll do that in some other videos. Okay. And using standard manipulations, we get so we're going to apply this operator, sort of factoring out this term over here. And this is equal to some constant, which we're not going to worry about. And then e to the minus I lambda over 4 factorial. The integral d4w. And then you can work with manipulate the sources. And d of x minus y is just the Feynman propagator for scalar particles. Okay, so we're looking for a connected diagram with 2 interaction vertices. And thus order lambda squared and 6 propagators. Those are the D's. So the term we are looking for and Z gives this if you look in the solutions in the back of the book to selected exercises. sort of a hint to get you started. So we're looking for 1 over 2 factorial minus I lambda over 4 factorial squared. So what we're doing is we're Taylor expanding this thing. And we're taking the second term in that Taylor expansion. So it's 1 over 2 factorial, that term squared. So the integral, I won't always put like double integrals with 2 integral signs, but I will for right now. So it's this to the 4th. And now we're going to apply that. We're taking this term over here. This term over here, we're going to Taylor expand that also. So we're going to apply that to, we want the second term because we want 6 propagators. And so we want the 6th order term. So 1 over 6 in the Taylor expansion minus I over 2 double integral d4x d4y jx dx minus y jy. Want this to the 6th. So you can see basically we're going to take 8 derivatives. Each derivative knocks off a j. So we have 2 j's to the 6th power is 12 j's, 12 sources. We knock off 8 of them, we're left with 4 sources, which is what we want. We have 2 incoming mesons and 2 outgoing mesons. And as I said, we want connected diagrams, so we don't want something like this. This is a disconnected, this is like a vacuum diagram. It's second order because there are 2 vertices and there are 6 lines, 6 propagators. 1, 2, 3, 4 on the left thing, and then there's the top and the bottom contribute another 2. So we don't want this. Okay. Now, so our aim is by applying all the derivatives to get the symmetry factor. And so let's tidy up our initial expression. We have lambda squared, 2 factorial, 4 factorial, 4 factorial, 1 over 6 factorial, 1/2 to the 6th. Then we have these integrals of d4w1, d4w2, del j w1 to the 4th power, del j w2 to the 4th power, times the integral dx dy jx dx minus y jy to the 6th power. Now, this is like an exercise. As a student, you're not going to really do this stuff. You could program this on a, Maple does functional derivatives. I'm sure Mathematica does also. And you could try and put this in Maple or Mathematica, or you could try and do it by hand. Really, the books that talk about symmetry factors like Czernecki, they give combinatorial arguments. Now, for the small symmetry factors, the combinatorial arguments are easy to follow. But I found, if you look in Czernecki's book, the more complicated the diagram, the harder it was to follow all the arguments on the symmetry factors. It just gets too confusing to me. I'm not, to be honest, combinatorics is not exactly my, it's not myself. It's not my strength, let's put it that way. And luckily, we have these Feynman rules. People like Feynman, Dyson, Schwinger, and all the people that followed them developing quantum field theory, they all derived these rules. When you hear the Feynman rules, people work them out. So you don't have to work them out anymore. You just got to follow the rules to get the diagrams. But it's good to do once or twice just to see where they came from. That's the purpose of this exercise. So I want to start. Let's first compute one derivative on one propagator. So let's take del JW2 the integral in dx dy jx dx minus y jy. So this is equal to the integral dx dy. When you take the general formula for this is just basic functional thing, del j of u del j of v is equal to delta, so four-dimensional, usually u minus v. This is our basic idea. So here we get the integral of dx dy del x minus w2 dx minus y jy plus jx dx minus y del y minus w2. And then working out the delta functions, it's just the integral dy dw2 minus y jy plus the integral of dx jx dx minus w2. Okay. And renaming variables, this is just 2 times the integral of dx minus w2 j of x. Okay. Also note, I'm not, dx minus y is equal to dy minus x. So in general. So this is our first formula when we take one derivative. Now let's take another derivative of it. We can't take a derivative with respect to j of w2 again, because then it would be d of w2 minus w2, which is d of 0, and we would end up with a loop instead of a connected diagram. So the only other derivative we can take is del j of w1 of 2 the integral of dx minus w2 j of x. And this is just going to be equal to 2 the integral dx del x minus w1 dx minus w2 is equal to 2 d of w1 minus w2. Okay, so we're going to need these two formulas later. The thing to remember about both of these formulas is they both have a 2. We get a factor of 2. Whether we take one derivative or two derivatives, we get a factor of 2. That will come in useful. Okay, so again, let's outline without the numerical factors, let's outline what we have, or what we are facing. We're going to have del J W1, and leaving out the integrals, because right now we're just evaluating the derivatives. Del J W2 to the fourth power. And then we're going to have 6 terms. So I'm just going to write them out schematically. JDJ, and 1 term, JDJ, 2 terms, 3, 4, 5, and 6. Okay. So, as I said before, we have 8 derivatives. 8 derivatives. Functional derivatives. To apply to 6 factors. Each one of these over here is a factor. So we can't apply any derivative more than once, because then we're going to get a loop. So basically what we're going to get is we're going to have 2 of the factors This is what I mean by a factor. 2 of the factors will have a j of W1 and a j of W2 of derivative, comma, and 2 of the factors will have just 1 derivative, and 2 will have 1 derivative, or will have a del JW2. Okay. So we have to count how many terms we will get. So I'm going to start with a combinatoric argument. And I'm going to check it with more of a brute force argument. So first we apply 4 del J W2 derivatives. Now we have to be careful, not to apply to the same factor more than once, because otherwise we get loop. we don't get a connected diagram. Okay. So what we're going to get, just writing it schematically, when I write W1, that means a W1 derivative was applied to it. We're going to get something like W1, 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 then no derivatives on two terms, then plus, dot, dot, dot. Then we'll have something like nothing on the first term, W1, W1, nothing on the fourth term, W1 and W1. So this would be like the first term, the first factor, these are the factors, or terms. This would be the third, fourth, fifth, sixth. Okay, so by symmetry, it will turn out not to matter which factors we keep. We want to keep just one generic term, but we need to know how many of them there are. So just with this, we have a total, it's very easy to see, 6 times 5 times 4 times 3. And to understand what's going on, remember when we apply the first derivative, we're going to get W1 plus so we're going to get 6 terms. Then when we apply the second W1, so this is the first W1 derivative, then when we apply the second W1 derivative, now this one's going to lead to 5 possibilities, and so they're all going to lead to 5 possibilities. So we get 6 times 5, and so on. When we do all 4 derivatives, we get 6 times 5 times 4 times 3. Now, so we have, after we do the first, in general, we have the generic term, which is just W1, 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 blank, blank. And we have 6 times 5 times 4 times 3 of them. Now we have to take, now we need to apply four W2 derivatives. Okay. So now to see what happens here, I have no idea why it does that, but we can do this in several different ways, but basically what we're going to have is 2 of the derivatives have to hit this part, and the other 2 just go into the blank. So we have, to see which W1s we hit, which factors we hit in the beginning, we have 4, choose 2. This is equal to 6. 6 ways to hit the generic term. And once we do that, the other 2, and then there's only one way to hit, both of these are hits, so that's all we get. But this isn't all the terms because this tells you where the derivatives are applied, but we still have complete freedom on which W1. Let's say we decide, we need to know on which in sequence to apply, in what order. Just think about this a little bit and you'll see. So this gives us another 4 factorial times. So the total number of derivative terms by my combinatoric argument is 6 times 5 times 4 times 3 times 6 times 4 factorial. And this is equal to 3 times 6 factorial times 4 factorial. I take a 2 from the 6 to make that 6 factorial, so I'm left with that. So this is the number of terms that we get, if we just brute force work out the derivatives. Now, when we hit a term, hit factor with derivative, we get a 2. As I showed earlier, remember equations, star and star star. So altogether right now we're going to get an additional 3 times 6 factorial times 4 factorial times 2 to the 6th. Okay, now I want to just show you more of a brute force thing, but I'm not going to write it out on the iPad. So this is what I did was I said, imagine we have 6 terms, and I want to show you if you do it like a tree, like in computer science, a tree. At the root, at the top, we have 6 factors, none of which have been hit yet. Then we apply del J1, and we can have 6 places to apply it, so that's 6 times. And then we apply del JW1 again. We're doing this 4 times, so we get 5, 4, 3. So that gives us the 6 times 5 times 4 times 3. Now it becomes a little more complicated. Now what I do is there are various ways to proceed which have different combinations. So let's say on the left, after I've gotten through the W1, 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 blank, blank, now there's 4 places that I can apply a derivative with respect to W2 on the first, the second, the third, and the fourth. And I'll end up with a generic term where when I have in parentheses, that means that's applied to one factor, where one factor has W1, W2. The first factor has 2 derivatives applied. Then I have W1, 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 blank, blank. Now, with that factor, I can apply another derivative with respect to W2. And now this one can go on the second factor. There'll be 3. It could go on the second, third, or fourth factor. So there's 3 of those where I'll end up with del W1, W2, W1, W2 on the first 2 factors, and then W1, W1, blank, blank. Then I apply another factor. I got 2 more factors to apply, and they go into the last 2 slots. I have 2 possibilities when there's 2 slots open, and 1 possibility when there's 1 slot open. Then if you go back up the tree, when I went with applying it to the W1s, I could have also applied it to the blanks. There were 2 blank spots to apply. And, so I get 2. And then I can, again, there's bifurcation. I can either apply it to the W1s, which are 3 of them, or I can apply it to that blank spot. So I don't want to go through all of this. I worked it out. You can follow it through. But here's the interesting thing. I can't get this to show. Anyway, the interesting thing is that all the branches after the 6, 5, 4, 3, there are 6 of them which have leaf nodes at the bottom of the tree. And all of them have the same number of combinatorics, but they're written in different orders. They're all 4 times 3 times 2 times 1. And sometimes they're like 4 times 3 times 2 times 1, and then 4 times 2 times 3 times 1, 4 times 2 times 1 times 3. and so on. So there's a total of 6 of them. So you get 6 times 5 times 4 times 3 times 6 times 4 factorial. That ends up giving the same thing that I had earlier. So if you look at the handwritten notes, you'll see a more brute force way to establish that this combinatorial factor that I got, 3 times 6 factorial times 4 factorial, is correct. They all have the same 2 to the 6th. Okay. So we're getting there. Progress is being made. Okay. So let's just write down again what we have now. We have lambda squared, 2 factorial, 4 factorial, 4 factorial, 1 over 6 factorial, 1/2 to the 6th, 3 times 6 factorial times 4 factorial times 2 to the 6th. Then I have the integral dw1 dw2 d of w1 minus w2 d of w1 minus w2. And then I have times the integral dx jx dx minus w2, square it, times the integral dx jx dx minus w1 square. These squared terms are the terms that had only one derivative hit it, and when there were 2 derivatives, we were left with just the dw1 number 2. So this is already, aside from the numerical factor, it's looking pretty nice, like a space-time diagram. If we were to like draw the Feynman space-time diagram corresponding to this, we get something like this. W2, W1. We have 2 sources. I'll use X for like the sources, and 2 sources coming out. But we can also have, there's no reason why this has to be W1. This could be W2 and so on. So we can also have W1, W2 sources. And we're doing bosons, so we would just add the amplitudes. Now, there's still an additional combinatoric factor that we have to work out. And one of the things we should do is we should put in what the source is. The source is something like del x minus x1 plus del x minus x2 plus del x minus x3 plus del x minus x4. In other words, we're just sort of going into the blob located at x1. So now we could actually label these points. Say x1, x2, x3, x4, x1, x2, x3, x4. And if we carry out the delta functions, if we substitute it in this, what we're going to get, and you can work out with the numerical factors, this is what all those factors above, all of these things, work out to. And then we get the integral dw1 dw2 dw1 minus w2 dw1 minus w2. And now what we're going to do is we're going to get like 4 terms. dx1 minus w1 plus dx2 dx2 minus w1 plus dx3 minus w1 plus dx4 minus w1. That's like one term. Then we're going to get dx1 minus, same term repeated. These are all multiplied. Now we get two terms where we have W2 instead. Now, not all of these will contribute. We have to get this diagram here. So to show you how many of these there are, it's not like 4 times 4 times 4 times 4. Let's say we start over here with this term. Well, if we have x1 connected to w1, the only other term in here with w1 that can be connected to x1 is x2 minus w1. And then from here we can go two places. We can go here, x3 minus w2, or we could go x4 minus w2. And once we do that, we're fixed on the last term. Only this will contribute to the connected diagram that we want. And it's easy to see when you analyze the other terms that you'll either get in this diagram or this diagram. And so this one has, I've drawn here, it has two terms corresponding to the first term. And each of the other terms is similar, so we get a total of 8. So now we get a combinatorial factor of 8. So I get 3 over 2 times 4 factorial times 8 times lambda squared the integral, and this is equal to 4 factorial is 24. So this is equal to 1/2. That's the symmetry factor that we wanted. dw1 minus w2, dw1 minus w2, dx1 minus w1, dx2 minus w1, dx3 minus w2, dx4 minus w2. So this corresponds exactly to these two diagrams in space-time. And so we've derived the correct symmetry factor. And for second order connected meson, two mesons scattering into two mesons. And if we substitute, I'm not going to do it. We substitute for the d's, the expression for the propagator, transform to momentum space via Fourier transform, and then finally amputate external legs. We get exactly what we wanted. M is equal to lambda squared over 2. The integral d4k, 2 pi to the fourth, 1 over k squared minus m squared plus I epsilon, 1 over k1 plus k2 minus k squared minus m squared plus I epsilon. Okay. So that's all I want to say about this. Again, as I mentioned earlier, one doesn't do this all the time and everything. One has a bunch of rules, and one applies to rules. One gets the diagrams right away. Calculating these loop diagrams, by the way, is often quite difficult, and that's more technology. Students sometimes ask me how hard is quantum field theory, and I often say it's an order of magnitude more difficult than quantum mechanics. Not because conceptually it's more difficult, but because there's all these like tricks and calculations and long calculations, and you have to develop things like path integrals, and you need to develop regularization and renormalization, things like dimensional regularization. So there's all these like long, deep calculations. That's conceptually it's no harder than quantum mechanics, but calculation-wise, becomes like an order of magnitude more difficult. Anyway, I will see you next time, where I'll try and do the second half of the Peskin and Schroeder Chapter 3 QFT blog. Thank you very much. Bye-bye.